Welcome to that of the UG and PG students for NET question solution 2024. Now we are going to that of the first questions regarding the pericyclic reaction, where the substrate cyclization reaction take place between that of the azo systems and that of the cycloheptene system, where the peripheral or molecular orbital are participate in the cycloaddition reaction. So we know that only the peripheral means terminal orbital are participate in the cycloaddition reactions. Here the terminal orbital is that we get that of the bicyclic system via the terminal orbital interaction, and here the internal orbital interaction we get that type of a bicyclic compound. But the possibility interaction is that the bicyclic compound produces the frontier orbital interaction by the suprafacial interaction to give the favorable interaction to give the product A. And here the 8 pi electrons are present, means 2, 4, 6, 8. 8 pi electrons are present, and here is the 2 pi electron, and the supra interaction will take place, and so the option A is the one is the correct, where the product A is formed with 8 pi electron suprafacial with the 2 pi electron suprafacial interaction. Here the inner orbital interaction does not take place. In the pericyclic reaction or in the cycloaddition reaction, the inner orbital does not participate in the cycloaddition reaction. Here the some examples has been taken from that of the Claydon book, where the terminal orbitals are participate in the cycloaddition reaction between that of the tropon system with the cyclopentadiene system, and we get that of the bicyclic ring system. Similarly, another Fulvin system and the diene also participate similar type of the cycloaddition reaction by the terminal orbital interaction to get that of the bicyclic compound. Here some interesting examples has been taken from that of the Claydon books, where the nitro compound react with that of the phenyl isocyanide derivative to that of the dipolar cycloaddition precursor, and which can add with that of the alkene in the same manner and produces the cycloaddition product. And these examples several times come in the NET examinations. Now the second problem is that of the elimination reactions, where the elimination reaction, the P substrate has the two eliminating group in the anti-periplanar orientation. We know that the stereoelectronic requirement for the elimination is that the two leaving group must be present in the anti-orientation. Here the hydrogen and the bromine present in the anti-orientation, so the hydrogen and bromine can eliminate it to give that of the acid ring derivative with faster rate. But syn elimination is not preferable, as the steric interaction will occur between the two leaving group and the base, and so the syn orientation, the concerted mechanism, does not take place, and hence the negative charge is created beta to that of the halogen atom, and this negative charge is stabilized by the phenyl ring conjugation and the elimination of the bromide to give the phenyl acetylene. So the syn substrate go through E1CV mechanism. In the E1CV mechanism, the first step is the reversible step. So the option 1 is correct, means the anti-elimination occurs in the faster rate compared to that of the KQ, means that for the substrate C elimination, and the substrate 1 undergoes E2 reaction, but the substrate 2 undergoes E1CV mechanism. This problem has been taken from that of the Claydon group, where the intramolecular lactonization followed by the E1CV elimination give that of the cyclic lactone product. Next is that of the conformation related problem, where the substrate A is formed by the reaction with 3O234 triphenyl butyric acid, and if we backward direction we get that of the starting material. This is the actually acylation reaction, intramolecular acylation Fidel-Cup reaction, where the benzene pi electron participate to form the intramolecular acylation reaction. And if we convert it to that of the Fischer projection formula, we get that this is the 3O substrate, and when it converted to that of the Newman projection, and when after front carbon 180 degree rotation and the back carbon 120 degree rotation, we get the a particular conformation which is matches with that of the option 2. So the option 2 is the correct. Here some examples have been taken where the intramolecular reaction take place via intramolecular heteroalylation reaction in presence of the Lewis acid, and we get that of the indole derivative where the indole substrate undergoes 3 position attack to give the spiro intermediate, and this spiro intermediate has two probability via the alkyl migration and the aromatization, and we get the two isotopic substitution distribution equally. This is the organometallic questions where the alkyl group is migrated same phase to that of the manganese and via the decarbonylation reaction. Here is the mechanism where the alkyl group is migrated same phase to that of the decarbonylation product, and we get the methyl metal bond, manganese bond, and a CO is eliminated, and this isotopic labeled CO group is further attacked to get the desired product, and this is matches with the option 1, so the option 1 is the correct. This is the aromaticity related problem where the Huckel aromaticity rule has been explained in the molecular orbital theory where the alpha is the repulsion factor and beta is the stabilization factor. From this alpha beta terminology we can detect the stability of the aromatic compound. In case of the cyclopropenyl cation, the alpha and beta can be distributed as alpha plus 2 beta for the down state and alpha minus beta and alpha minus beta for the anti-bonding molecular orbital. And here the 2 electron is present, so if we calculated the alpha beta term for the stabilization, we see that the 2 alpha repulsive factor is nullified by the 2 beta attraction factor, and only the 2 beta stabilization factor is remaining, and that stabilization factor stabilizes the aromatic molecule. Similarly, the benzene molecule can be distributed in similar way where the ground bonding molecular orbital can be distributed as alpha plus 2 beta and alpha plus beta, and the 2 electron for each molecular orbital, if we counted it, and we get that 6 alpha and 8 beta. Here the 6 alpha repulsive factor is nullified by the 6 beta attraction factor, and hence the 2 beta is extra, 2 beta is the stabilization factor, and this is counted as a resonance energy for the aromatic benzene compound. Now this is related to the photochemistry related problem where the photochemistry we know that the compound undergo Norris type 2 reaction where the beta cleavage occurs. Here the substrate after beta cleavage produces the trans alkene, and in the substrate if we take that of the trio compound, and after the beta hydrogen abstraction and the beta CC bond cleavage, we see that the alkene is formed, and this alkene is the cis alkene, but the given problem the alkene is the trans alkene. So after the CC bond cleavage, the erythroisomer is the proper stereochemical conformation, and we get that of the trans alkene, so the erythroisomer gives the product via Norris type 2 reaction. This is the problem where the asymmetric aldol reaction takes place via Zimmermann-Traxel model. In the Zimmermann-Traxel model, where the carbonyl group and the enolate ion can approach in the fashion in the chair conformation, where the alkyl group is present in the equatorial position. Here, in the given compound is that of the trans aldol, means the trans aldol product, anti-aldol product, and we get that this is the anti-aldol. And if we see the similar type of that of the Zimmermann-Traxel model, if we project it in that fashion, where the tertiary butyl group and the methyl group present in the anti-orientation, here the tertiary butyl group, methyl group present in the anti-orientation, in the 6-member cyclic transition state, where the tertiary butyl group and the methyl group present in the anti-orientation, and if we project it in that way, and after the intermolecular addition, we get the stereochemistry where this is the front carbon where the methyl group present in the axial orientation and the hydrogen group present in the above orientation. Similarly, this is the back carbon where the phenyl group present in the axial and the hydrogen group present in the left side, and this is the OBF3. And when it rotates around at 120 degree, then we got the conformation, and after 120 rotation we got the conformation which is matches with the option 3. So the option 3 is the correct option for the formation of the product anti-aldol. This is the intermediate transition state for the anti-aldol product formation. This is the problem of the electrocyclic reactions, where the alkyl group is taken as considered as the R group, and this R group is similar with that of the bromine, where the bromine and the alkyl group in the same side, and here RR and the bromine is in the same side. When it undergoes disrotation ring opening, it gives that of the V-shaped, and this is the V-shaped or U-shaped conformation, where the ring formation is the more favorable, and hence the bromine elimination is more favorable, and we get this product. So the option B is formed as the major product via disrotating ring opening. This problem has been taken from that of the Claydon books, where the electrocyclic ring opening followed by ring closing, we get that of the product. This is the interesting problem where the electrocyclic reaction followed by cycloaddition reaction take place. This is the 13C NMR problem, where the 13C NMR gives that of the different type of the phosphorus compound, where the P4 stain, this is the structure of the P4 stain, where all the phosphorus atom is in the symmetrical. So it gives the singlet peak, and this is the peak, and this is matches with that of the P4 stain. And the structure of the P4S3, where the two type of the phosphorus atom present, one is the present in the triangle, another is the present in the apex. So here this phosphorus is splitted by the 3 phosphorus atom as a quadrate, and this 3 phosphorus is splitted by the 1 phosphorus as a doublet. So this is the P4S3, where the A splitting pattern is observed. And in case of the P4S7, where the 2 type of the phosphorus is present, one is the 2 type, another is also 2 type, and both are present as a triplet and triplet. This is the C. So the option 1 is the correct. This is the problem of the 1-inch NMR spectra, where the beta lactam unit, where the HB, the signal corresponding HB means this is the HB proton. We know that this HB proton is not attached with that of the electronegative element. So this electronegative carbon element, so this HB proton is comparatively lower chemical shift. Hence, the option may be between that of the 3 and 4. And from the splitting pattern option, we can see that in case of the HB, that HB it appear as a doublet and doublet, where the both are in the trans orientation, so the coupling constant value in both cases will be small. Here the J equal to 7.0 and J equal to 2.5 Hertz. Here the coupling occurs between that of the HA and HB via 7.0 Hertz, and the coupling occurs between that of the HB and HC is only 2.5 Hertz. And this coupling constant is lower due to the lowering of the dihedral angle, and it is mostly belong with that of the 60 or 70 degree. Next, in case of the HE, where HE also is not attached with that of the electronegative element, but here the geminal coupling will occur between the HD and HE by the coupling constant 18 Hertz, and similarly HC and HE is coupling constant, smaller coupling constant, lowering of the dihedral angle. So this will be the lower chemical shift, and the geminal coupling constant lead to that of the higher coupling constant. So the option 4 is the correct. This is the problem of the metathesis reaction. In the metathesis reaction, this is the in-ion metathesis, where the in bond first coupling with that of the second generation Gibbs catalyst to give that of the olefin carbene complex, metallocarbene complex, and this metallocarbene complex undergoes 2+2 cycloaddition reaction and give that of the another metallocarbene intermediate. When this metallocarbene intermediate attached with that of the alkene system, we get that of the desired product, and this desired product matches with the option 4. So the option 4 is the correct option. This is the rearrangement problem. This is the Wagner-Merwin type rearrangement, where the tertiary center, 3 degree center is attached with that of the hydroxy. After the protonation of this hydroxy, the methyl group is migrated, which is anti to that of the hydroxyl group, and we get a carbocation, and then the alkene is formed, and after the elimination of this alkene, we get that of the bicyclic alkene, and this bicyclic alkene, after cleavage of the osmium tetroxide hydroxylation, cis hydroxylation, followed by sodium iodide perhydroxylation, where the cleavage of the diol takes place, and to get the product which is matches with the option 3. And this problem has been taken where the Wagner-Merwin type rearrangement takes place by the ring extension, and where the 4-member ring can stabilize by the 5-member ring formation. This is the Hammond equation problem. We know that in Hammond equation, the rho value can determine the transition state. In case of if the rho is more less electron dense means that this is the acyl chloride, where the acyl chloride can added with that of the amine to give that of the amide product via this intermediate. And this acyl chloride has highly electron deficient, so electron deficient transition state has lower rho value. A positive rho value means more electron in the transition state, but in the negative rho value means fewer electron in the transition state. Here the acid chloride has fewer electron, so it has large negative value, and hence the large negative value means this amide can couple with that of the benzoyl chloride to give the amide derivative with the lower negative, higher negative value means minus 2.98, and this is the SN2 reaction where the phenoxide ion can attack with that of the alkyl iodide to give that of the ether derivative, where the electron is away from the system, where the electron density is lowering, and hence this is the negative, but this will be lower negative value in the transition state, so it will be the option 2 is the correct, where the A is matches with that of the minus 0.30, and the B is matches with that of the minus 0.95, and C is matches with that of the option 2, and this is the E option, where the lower electron at the transition state lead to that of the higher rho value. Thank you for watching this video.